Hello students, my name is Shashank Shekhar. So till now we have seen the electronic configuration of all the elements in the long form of periodic table. Now we will try to divide the elements on the basis of the orbital in which their last electron goes. Okay, so on that basis we have four blocks: S block, P block, D block and F block. The above principle, which is also called as the build-up principle, okay, electronic configuration of atom provides the theoretical foundation of the periodic table. Elements in a vertical column of the periodic table constitute a group or a family and exhibit similar chemical behavior. The same thing written that if we move along the group, they have the same electronic configuration and they kind of exhibit similar properties. The similarity arises because these elements have the same number and same distribution of electrons in the outermost shell. Now, if I try to just divide it, so this is the overall picture. On the left side, in which the s orbital is filled, 1a and 2a, or one group 1 or group 2, they are called as s block elements. On the right hand side, we have 3a, 4a, 5a, 6a, 7a and 8a. Okay, they are called as p block elements, or you can also call them as 13, 14, 15, 16, 17 group. So this both s and p block, they constitutively make the what? They make the main group elements. Okay, now in this section, which is called as transition elements, there are exceptions, which all the elements are not called a transition element. We will study about these exceptions in the 12th class when we will study D and F block. But for now, let us consider that they are present in the D block. So we start from 3B and then end up at 2B, right? So we start at 3B and end up at 2B. So I think something is wrong here. So here it will be 1A, 2A, 3A. Yeah. Okay. Now we will name this group as 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in the modern terms. Okay. So this all are D block elements in which the D subshell is progressively filled. There are some exceptions to that, but in this case, D orbital is progressively filled. And here is the F block element, or the inner transition element in which the F orbital is filled. Clear? Or F subshell is filled. Now this classification is again totally on the base of the atomic orbital that are filled with electrons, which has S, P, D and F block. Now, if I talk about the general electronic configuration, so in S block we have NS 1 to 2. So this is the general electronic configuration, valence electronic configuration. For P block element, it is NS2 NP 1 to 6. Okay. For D block elements, it is N minus 1D, and D can be 1 to 10, NS 0 to 2. F block elements, N minus 2 F 0 to 14, N minus 1 D 0 to 10, and NS 2. So these are all the general electronic configuration. Here it will be 0 to 10. Okay, it will not be 0 to 1, it will be 0 to 10. Now, two exceptions are there in the categorization. So helium belongs to the S block, but it is positioned in the P block. Okay, so if you see here in the periodic table, yeah, here you can see that helium is placed here. It is in the P block, but the electron is going to the S orbital, right? So this is an exception. Next is hydrogen has only one S electron and it can be placed in alkali metal or halogen atom both because of the similarity in properties. Okay, so that's that reason it is placed at the top. Okay, here it is placed because place is not fixed because of the difference in electronic configuration and the physical and chemical properties. Now, what are the general characteristics of S block elements? So they are soft metals with low melting and boiling point. They have low ionization enthalpy, are highly electropositive. So we will study this, what is ionization enthalpy and all, in the upcoming classes. So if I give you a small idea, it is basically the energy required to remove an electron from an element in its gaseous phase. Okay, so they are highly electropositive, so therefore they can easily donate its electron. Now they lose the electron readily to form +1 and +2 ion. Okay. For that reason, since upon losing 1 or 2 electrons, it easily forms the noble gas configuration. For that reason, they are called as reactive metals also. Okay, the metallic character and reactivity increases as we move down the group. So as we move down the group, the reactivity increases. What is the reason behind it? Because the size of the atoms increases, and hence it is now easier to remove an electron from the outermost shell because it is away from the proton. So the influence of proton is less because electrostatic interaction is the basis of this formation of atom. Okay, now this force of attraction is inversely proportional to distance. So as the number of cells increases, the electrons are filled in the outermost shell. Therefore, the pull of the atoms towards electron decreases, and therefore it can easily donate electrons and hence are metallic in nature. The compound of the S block element, with the exception of beryllium, are predominantly ionic. So except beryllium, all the S block element forms the ionic compound. Most of the metals of this block impart characteristic color to the flame. They are a strong reducing agent. Okay, all are good conductor of heat and electricity. So these are some properties of the S block elements. Okay, so these are some properties of the S block elements. Now, S block elements, we have seen that they consist of two groups, group 1 and group 2. Group 1 is called alkali metals. Group 2 is called alkaline earth metals. Group 1 has the stable oxidation state of +1, whereas group 2 has the stable oxidation state of +2. Why is it so? Because after losing one electron, the alkali metal becomes a noble gas. Okay, it goes same for the alkaline earth metal. So if it loses 2 electrons, which is present in the s orbital, they become noble gases, right? Now, alkali metal are characterized by the low ionization energy because upon the removal of one electron, they quickly go to the noble gas configuration, and due to this reason, they are having very low ionization in the energy. Okay, so why don't alkaline have so? Because after removing one electron, it does not goes to noble gas configuration. We have to remove one more electron from there. Okay, and removing from one electron from positively charged cation is very difficult. So they have low ionization enthalpy. Okay, low ionization energy, low melting point, boiling point, soft texture. Okay, silvery white in color and reactive with water. So they are very reactive. They can even react with water. So sodium, if you just put it in oxygen in free atmosphere, it will catch fire. It is that much reactive. Not talking about alkali earth metal, so they are harder than alkali metals and have higher melting and boiling point. They react with water less vigorously. Okay, they react with water less vigorously. Okay. Now next, let us move to P block elements. Okay. So if I talk about the P block element, so P block element includes both metal and non-metal. See, okay, they include both metals and non-metals, and the number of non-metals is higher than that of the number of metals. Further, the metallic character increases from top to bottom. Okay, it increases from top to bottom and increases from left to right. The non-metallic character increases from left to right, whereas the metallic character increases from top to bottom. Their ionization energy are relatively higher as compared to those of S block element. Clear? Okay. The reason is very obvious, because in S block element it is easier to gain the noble gas configuration by removing very less number of electrons. They mostly form covalent compounds. So if we move from left to right, so in S block element they are much more metallic in nature, whereas as we have moved from S block to P block, left to right, the metallic character has decreased, right? Okay. Now, some of them show more than one oxidation state. Okay, so in case of P block element, they don't show very much number of oxidation state, and same goes for S block element. They have only one oxidation state, although P block element can show some variable oxidation state, but it is very less as compared to the D block. Their oxidizing character increases from left to right. So oxidizing character is basically, it is the number of means it will get reduced. It means it will gain electron, right? So as we move from left to right, the oxidizing character increases because they can gain electron and go to the noble gas configuration. So we do it from left to right, and it oxidizing character increases, whereas the reducing character means the tendency to give electron decreases from top to bottom in the p block. What about the location? So they are located in group 13 to 18, okay, including helium. Half have varying oxidation state and exhibit a wide range of chemical properties, including metallic and non-metallic character. Now, group 13 elements are commonly known as boron family. Now we will study each of these groups individually. First, about group 13. So group 13 are called boron group and are characterized by the ability to form covalent compound, right? Whereas group 14 elements can form covalent compound and also exhibit allotropy. So what is allotropy? So basically it is the property of the element to exist in multiple states. Okay, like carbon has allotropes of carbon include graphite and diamond, Buckminster Fuel length, which is C14. So carbon is the most say excellent in making this allotropes. They exist in the form of graphite and diamond. Talking about the group 15 elements, they have diverse properties and include non-metals like nitrogen and phosphorus, and metalloids like arsenic and antimony, and a metal that is bismuth. So they have very diverse property. So they include starting from non-metal, going to metalloids, up till bismuth, which is a metal. Clear? Okay. Now, group 16 elements are non-metallic except for the heavier members like tellurium and polonium. So they are non-metallic in nature. But there are exceptions, of course, because as the size increases, their metallic character increases. Group 17 elements are highly reactive non-metal that typically form diatomic molecules. We know them. They are chlorine, fluorine, bromine, and iodine. They all are under group 17 element. They are called as halogen. So first we have boron family, then we have nitrogen family, then we have oxygen or chalcogen family, then we have halogens. So they are very reactive. Why? Because upon gaining one electron, they go to noble gas configuration, or they attain noble gas configuration. What about group 18? So group 18 are the most stable, least reactive element due to their complete balanced shell. So they exist as monoatomic gases. Okay, so helium and all exist as monoatomic gases. They don't exist as He2 or aren't radon 2, or you can say boron, nitrogen, fluorine, neon 2. Okay, so they can't exist as diatomic gases because their octet is already filled. Now there are exceptions to it. They can form bonds, like xenon can form bonds with oxygen. So we will look at that exception later on. Now what are D block elements? So D block elements are typically metal, and they have all the typical properties of metal, like they are hard, malleable, means they can be beaten and converted into sheets. Next is they can be drawn into wires and with high melting and boiling point. Next is they are good conductors of heat and electricity, right? Their ionization enthalpy are between S and P block elements. Okay. Now they show variable oxidation state, so they can show a variety of variable oxidation state, right? They can go from +2 to +7. So they are the best in showing the variable oxidation state, and they can form both ionic and covalent compound. Clear? Okay. Now their compound are generally colored and paramagnetic in nature. They form colored complexes. Most of the transition element, such as vanadium, chromium, manganese, iron, cobalt, nickel, copper, and their compound are used as catalyst. Because of their variable oxidation state, they can be used in various purposes, right? Clear? Okay. Now most of the transition element form alloys also. Okay, we have the alloy say cast iron and all. They are all alloys. Now zinc, cadmium, and mercury, in which the d orbital is completely filled, they do not show the properties of transition element, because transition elements are those, or the d block elements are those in which the d orbital is incompletely filled either in their atomic state or in their ionic state. So they don't have the incomplete incomplete field d subshell either in their ionic state or in their atomic state, both, right? D block elements, also called transition metal, located in groups 3 to 11. So they are in the group 3 to 11. They are mostly lustrous, hard, dense metal with relatively high melting and boiling point. Transition metal exhibit variable oxidation state and can form colored ions that play significant roles in catalysis and pigment formation. And biological systems, they have filled d subshell and form many coordination complex with various ligands. Okay, due to the filled d subshell, the involvement of d orbital, they can form complex with various ligands. What are the general? Now moving to general characteristics of F block elements. Now they are heavy metals. They have high melting and boiling point. They show variable oxidation state again. Their compound are generally colored. They have a high tendency to form complexes. Most of the elements are actinides. In actinide series are radioactive. So this is one point. Now they are also known as inner transition elements. They are located in the downside of the periodic table. We have seen them. They are actinoids called length and actinoids starting from 89 to 103. Lanthanoids were going from 57 to 71. Now these elements are radioactive in nature, including actinoids and all, have high densities, and chemistry is dominated by the F electron. Now lanthanoids are characterized by the similar properties which is attributed to the gradual filling of their 4f orbital. Actinoids have a very wide range of properties, including some radioactive elements such as uranium and plutonium. Clear? Okay. Now we will see this S block and P block and D block in one go, in a kind of revision thing. So they are all reactive elements, have low elimination enthalpy. They form +1 and +2 oxidation state, metallic in nature, and are highly reactive due to and never found in the pure form. The compound of the S block element, with the exception of those of lithium and barium, are predominantly ionic. We have seen this. P block elements are also called the representative element or the main group element, in which we have configuration varying from NS2-NP1 to NS2-NP6. At the end of each period is a noble gas. We have seen all the orbitals in the valence shell are completely filled by the electrons, and it is difficult to alter their stable arrangement by addition or removal of electron. Preceding the noble gas family are two chemically important groups of nonmetals. Now group 17 are called halogens, group 16 is called chalcogen. These two groups of elements have high negative electron gain enthalpy and readily add one electron because they gain noble gas configuration, and they are non-metallic in nature as we move from them. D block elements start from 3 to 12. Okay, and they are characterized by the filling of d orbital. Exceptions are palladium, in which the s orbital is not filled, which is 4d, 10 and 5s0, and they are all metals. They mostly form color compound. Okay, they have the catalytic property, whereas zinc, cadmium and mercury don't have any. They are not considered as d block element because they have not complete filled d orbital. In a way, transition element form a bridge between the chemically active S block and the less reactive elements of group 3 to 14. Therefore they are called as transition element. The inner transition element, which include lanthanoid starting from cerium to lutetium, 58 to 71 is atomic number, and actinoid starting from thorium to lawrencium, which is Z is equals to 90 to Z is equals to 103. They are characterized with the general electronic configuration, which is N-2 F14, F1 to 14, N-1 D0 to 10, NS2. Last electron add to the element in each filled f orbital. Hence, they are called the inner transition element. Now, properties of element within each series are quite similar. Chemistry of early actinoids are more complicated than corresponding lanthanoid due to large number of oxidation states possible for this actinoids element. Actinoids elements are radioactive in nature. Elements after uranium are called trans-uranium elements. Many of the actinoids elements have been made only in nanogram quantity, so they are very, very reactive in nature. What are the defects in the long form periodic table? So although it is nearly perfect, but still it has some defects. So we'll study those defects now. The first defect is that the position of the hydrogen is still not settled. Although they are placed alongside with the metals of group 1, halogens in group 17, since it shows similar properties to both alkali and Halogens, lanthanoids and actinides have not been accommodated in the main border. Okay, so it is placed in the separate panel on the downside. Next is the element Z is equals to 117 and 120 have not yet been discovered. In which family or group would we prefer this element? So, if you talk about the Z is equals to 117, then it can have the electronic configuration of 5f14, 60, 10, 7s2, 7p5. Okay, so it will in the group 70. Whereas the element with Z is equals to 20 will be placed in group 2, which because the electronic configuration is 8s2. Clear? Now, in addition to the displaying the classification as SPD, there is another band of classification on the properties. They can be divided as metals and non-metals. Metal comprises of more than 78 of all known metals appear to the left side. On the left side, we have mostly metals. Metals are usually solid at room temperature. Exceptions are mercury, gallium and cesium also have very low melting and boiling point. These are some exceptions that we talk about. So they are metals and S, P, D, and F. So here is a complete diagram of that. Metals usually have high melting point and boiling point. We know it. They are good conductors of heat and electricity. They are malleable and ductile. Right? They are malleable and ductile. In contrast, non-metals are located at the top right-hand side of the periodic table. In fact, a horizontal row, the properties of elements changes from metallic on the left to non-metallic on the right. Okay. So as we move from left to right, the metallic we see that the periodic the metallic character decreases from left to right. Next is non-metals are usually solids or gases at room temperature with low melting and boiling point. They are poor conductor of heat and electricity. Most non-metallic solids are brittle or neither malleable nor ductile. The element become more metallic as we go down the group. The non-metallic character increases as one goes from left to right across the periodic table. Right. The change from the metallic to non-metallic character is abrupt by a zigzag. See, as we go from left to right, so this is metallic, this is non-metallic. Blue is metallic, right is green is non-metallic. Now this creates a zigzag pattern, right? So in between we have a metalloid. So these all are metalloids: silicon, germanium, arsenic, antimony, tellurium, plutonium, and actinium. Right? Not actinium, instantinium. Right? They all are metalloids. So they create a zigzag between the metals and the non-metals. Now they are called as semi-metals or metalloids. Clear? Okay. So this was all for today's lecture. With this, I end my lecture. Thank you.